Okay, today's topic is ideal filter as non-causal, and we'll also see digital filter specification. So our topic is and digital filter specifications. This entire process we will discuss for FIR filters, that is called finite impulse response filters. So before going forward, we'll just do some revision, so that will be helpful to us for what we have learned till this point. First is, by general difference equation, transfer function hz is equal to summation of k equals to 0 to m bk z minus k over 1 plus summation k equals to 1 to n ak z minus k. Now, FIR filters are without feedback. That means n is equal to 0. So hz is equal to summation k equals to 0 to m bk z minus k. Then by equating to yz over xz, we can find out yn equals to summation k equals to 0 to m bk x n minus k. Right? Now if we want to realize this particular system, we have an input xn goes through a delay unit z inverse, then again z inverse, z inverse, z inverse, and then this xn multiplied with v0, first keep 0, v0, then v1, v2, and at last vm, and this all are added together will yield yn. One can clearly see there is no feedback in this particular system. So FIR is this kind of system which doesn't have any feedback from the output side. Now if we put xn is equal to delta n, then the output is yn equals to hn, because hn is impulse response. Then hn will be equal to summation k equals to 0 to m bk x n minus k, which is equal to b n. Now that is we know n varies from 0 to m. So the impulse response of the system is finite. FIR only have zeros, no poles. That's why sometimes called all zero filter. One can see FIR does not have any kind of feedback, so FIR also another name that is called FIR is also called feed forward non-recursive or transversal filters. Another important property of a FIR filter is a FIR filter cannot be directly derived from analog filters. Now we have actually seen this particular example in lecture number 8 when we have used RC filter as LPF. RC filter as LPF in lecture 8. Right? In that particular case, the transfer function we got Hz is equal to 1 minus alpha over 1 minus alpha z inverse with ROC mod z greater than alpha. In this transfer function, the value of alpha is equal to e to the power minus t by RC, where t is equal to 1 by fs, where fs is sampling frequency. One can see in this filter we have only poles and we also have feedback with this system which we have implemented in the lecture number 8 and we have designed that particular realization. So in that particular case we have seen that there is a feedback involved. So this particular filter is IIR, which we have discussed in lecture number 8. Now another important point from a FIR filter is we have discussed in last lecture is about symmetric and anti-symmetric filters. So with that property, for type 1 filters which can have response for high frequency and as well as low frequency are the most versatile filters. Whereas type 2 filter shows response 0 at omega is equal to pi. That is, this filter is not suitable for HPF, high pass filter. Then we have also seen type 3 filter. Type 3 filter has an asymmetric sequence as well as odd sequence. So that's mean response is 0 at omega is equal to 0 and omega is equal to pi. That's mean type 3 filter is not suitable for HPF or LPF. But the type 3 filter introduces a phase shift of pi by 2. Right? With the symmetric filters, we have seen there is a phase shift of pi by 2 involved. Now another case is type 4 filter. We have already seen these kind of filters, so we are just summarizing the particular relations to get the most out of those relations. Type 4 filter frequency response is 0 at omega is equal to 0 and thus not suitable for LPF. Now one can clearly see type 4 filter is not suitable for LPF, type 3 is not suitable for LPF, type 2 and type 1 are suitable for LPF. That's mean if you want to implement an LPF, low pass filter, we have to go with the symmetric sequence, either odd or either even, right? But if we want to implement a high pass filter, then we have to either go with type 1 filter or type 4 filter. Type 1 filter is suitable for both high pass filter and low pass filter, whereas type 2 filter is only suitable for low pass filter. But it is actually not suitable for high pass filter, but it can be used with band pass filter or other stuff. But it is not suitable for high pass filter. Whereas type 1 filter is the only filter which can be used anywhere, right? Similar as the case of type 3 filter, type 4 filter also introduces a phase shift of pi by 2. Okay. These two filters are from symmetric and this for anti-symmetric. Okay. So we have discussed till this particular point, and after this we'll start forward using these points and this discussion as our basic part. Now we want to design an FIR filter, but till now the specifications and all the details we have is of ideal filter, and if we want to see that particular case, we'll just write one by one all those things which we know, and then we will move towards the points till the point the filter is able to be realizable, and also it has causality in nature that we have also already discussed with the ideality part. The problem is with the ideality that it should not be a non-causal, right? So we will move ahead with the ideal filter and then tends towards the point such that we make a filter which can be realizable, right? So we can write a function hdz which is defined from n equals to minus infinity hn z to the power minus n. Now if we evaluate as dz at unit circle, right, then only we can put z is equal to e to the power j omega, and for this particular case hd e to the power j omega or h omega will be equal to summation n equals to minus infinity to infinity hn e to the power minus j omega n. Right, now we know the frequency response of discrete time signal is periodic, right, that we have already discussed in previous classes. Then hn can be obtained by Fourier series coefficient, right. Then we can find out the value of this should be h, because it is hdz, this should be hdn, right. So then we can find out the value of hdn. Then hdn by Fourier series coefficient will be equal to 1 by 2 pi minus pi to pi h d omega e to the power j omega n d omega. Normally realization is performed for the magnitude, right, but if we see this particular part, hdn is defined from minus infinity to infinity. That's mean we have hit a wall, right. The problem is we cannot realize any system from minus infinity to infinity because it will involve non-causality, and thus the system cannot be realized. That's mean that is such filter is non-causal and that cannot be realized. Now to remove this particular problem, what we can do is apply a basic mathematical proposition that first we short the impulse response. Which is going from infinity, minus infinity to infinity, we will short this impulse response to some point, right, and it is called shortening the impulse response. Truncation, or most popularly windowing, right, impulse response of the filter. Second problem, we want to make our system causal, right. We will short the sequence, right. We cannot realize a system which is going from minus infinity to infinity. That is one problem, because it is not summable, then it is a problem. Another problem is because it is going from minus infinity, it's starting from minus infinity, it has already have an input before we are applying, it is already having an output before we are applying any kind of input. That's mean we have to delay the sequence, right. So second point is delay the sequence to make it causal. Now these are the two problems we are facing with the ideal filters. Now if we can substitute this particular two propositions and implement in ideal filter, we can definitely realize any kind of filter with this particular properties. So this is the design process. First, we will shorten the impulse response of the filter, right? And then we will delay the sequence such that the sequence will be causal in nature. Okay. Now we will start one by one. First, we will start with the windowing technique. Right. First, we will start with the windowing. That's mean truncating the impulse response of the filter to some measurable value. Previously it is going from minus infinity to infinity. Now we want to truncate it and make it up to some measurable value, right? That is the most obvious thing we can do, measurable value. So what we can do is we can multiply the filter impulse response with a window function, right? So we can do a multiplication process and that will lead to a function which is truncated. So we will call this as htn, which is equal to hd of n into wn. We know hdn is defined from minus infinity to infinity. So in this particular case, our window function wn will be defined as 1 from minus n to n and 0 elsewhere. Then htn is equal to hdn from minus n to n and 0 elsewhere. If we apply this particular system, what we get is an truncated response of the filter which is only defined from minus n to n, right? Now one can see that we have truncated an infinite sequence into some finite sequence that is obviously having some impact over its frequency response, right? That we will discuss. So but first part we want to discuss is what will be the error, what will be the error part and how we can control that particular error, right? So we want to see that particular case and we want to find out the case for minimum error over the area, right? We want to find out case for minimum error over the area that is integral square error, right? We already knew hdn, discrete Fourier transform, leads to hd omega. Similarly, for htn we will have ht of omega. We already know for this particular this omega sequence will be continuous in nature, whereas this one is a sampled sequence, right? So the minimum error over the area, that is integral square area, can be determined using Parseval's relation, right? That is error equals to 1 by 2 pi minus pi to pi hd omega minus h t omega square t omega. Now one can clearly see this is the relation of Fourier series. So it is equal to, equivalently can be written as n equals to minus infinity h d omega as h dn minus h tn square. Now if we open this relation, htn is only defined from minus n to n. So we will write it in that particular sequence that n goes from minus n to n, and in that particular case hdn minus htn square plus summation n equals to minus infinity to minus n minus 1, that is hdn square plus summation n equals to n plus 1 to infinity hdn square. Now one can clearly see this error can be minimized only when, right? It cannot be 0 because there is a component of hdn here. So it depends upon that particular truncated part. So obviously hdn cannot match exactly the hdn part. So there will be some error. But this error can be minimized only when only when hdn will be equal to htn or htn will nearly follow hdn, right? In minus n to n. One can see if their sequence is exactly same, then error is the minimum error. As this deviation increases, the error also increases. One can say when htn or hdn will follow each other or htn will follow hdn, the error will be minimized, then there will be less error. Now after truncation, we are also proposing for the causality. We want our sequence to be causal. So that's mean delaying the sequence or impulse response so it is causal. Now that's mean we have already truncated sequence htn, then hn is the delayed sequence will be equal to ht n minus n, because it is minus n times in the negative domain. So if we will shift by the minus n, then it will start from the 0. So this is the minimum delay we have to provide to make the system causal. Now if we will take the jet transform of the sequence, it will lead hn as hz, ht as ht of z with z to the power minus n. And realizing sequence at unit circle, z will be equal to e to the power j omega. So h of omega will be equal to ht of omega e to the power minus j omega n. Now after this particular point, one can clearly see two things. First, delaying operation does not change the magnitude. right? That's mean if we delay a sequence, there will be no change in the magnitude portion will remain same, but delaying operation will modify the phase as this exponential minus j omega n term is now involved. This exponential minus j omega n term will get add on or subtracted, whatever the case, with the phase of the h t omega and lead to the change in the phase by this omega n. Then one can say design process for FIR filter involves truncating the infinite length impulse response Hn of ideal filter and then shifting such response to make the filter causal. Now one may ask why we want to make a FIR filter. For that we have already discussed certain points in the previous lecture and I will address those particular points right now also. So to make things a bit more comfortable and understandable. First point is FIR filters have a linear phase response. Now what linear phase response do is linear phase response ensures there will be no distortion. There will be no distortion among the frequencies in the delay portion. All frequency will face a similar kind of delay. Secondly, an FIR filter is much more stable in nature compared to the IIR filters. Obviously, implementing FIR filters much more costlier in terms of complexity and mathematics, but obviously its advantages are far more superior compared to IIR. Now it depends upon the application if you want to go with the IIR filter or FIR filters. We will discuss details about FIR filters in further lectures. Thank you.